Okay, here are some more notes on section 4.3, and this is a theorem 5. This is called the second derivative test for local or relative extrema. So how are we going to use the second derivative test? Well, that usually tells us about concavity. So we'll go over this statement, and what they're saying is, this is theorem 5 again, the second derivative test for local or relative extrema. If f prime of c equals 0, that means we have a horizontal tangent. That means it might look, well, either like this or like either like a U or a kind of a curved top, or a dome or an N, right? Like I should say either like this or like this. If f prime of c equals 0, so this is my function, and the derivative is 0, that means I've got a horizontal tangent. And if f double prime is less than 0, now remember, if it's less than 0, if the second derivative is negative, then we say it's concave down. Down for negative, or a little sad face. And up, it's concave up for when it's positive, a little happy face. You can think about it like that. Okay? So, this is concave down if it's negative. Sometimes we say don't be so negative because you're frowning. So hopefully that will help you remember. So if the second derivative is negative, but we have a 0, we have a horizontal tangent, then it looks like we have a local or relative maximum at x equals c. So that's all they're saying. So if we have a horizontal tangent and concave down, we have a relative or local maximum, right? And also if we have a horizontal tangent and it's greater than 0, if the second derivative is greater than 0, that means it's positive. That means we got a happy face because we're positive, or it means we're concave up. Then f has a local minimum at x equals c, because you can see it's a minimum right there, because it's the bottom of the smile. And this is the top of the frown, so to speak. So hopefully that will help you remember. All right, so if the second derivative is negative, we're concave down. That means we've got a relative maximum. If it's positive, that means we're concave up, means we have a relative minimum. So they kind of flip around a little bit, so you have to kind of think about it. So if you draw a little sketch like this, I think that would help. Okay, so here's an example. I came up with an example here. I'll find the local extrema for this, and we're going to use the second derivative test. And then sometimes it's a little bit easier to do that, and you'll see why in a moment. So first of all, we're going to do the first derivative test to find out, or we'll find the first derivative anyway to see where we have places where the derivative is equal to 0 or undefined. And let's say f prime of x. If we take the derivative of this, we're going to get 3x squared over 3, which is just x squared, minus 2x squared over 2, which is just, 2x over 2, which is just x, and minus 20. Okay? And we can tell that f prime can be equal to 0. It's a polynomial, so f prime will not be undefined. So we don't have any critical points that are corners or things like that, or cusp. But we can say that this is equal to 0. So if we set it equal to 0, we can factor it and set each factor equal to 0. And that would be x and x. And remember, the signs are different. Sign large and negative, so I can say negative, positive, and multiply to give 20, 5, and 4. Now we always want to check this because we've had some problems before with these. This is negative 5x plus 4x is negative x, and that's negative 20. So that's good. So we have x equals 5 or x equals negative 4. So those would be the points where my f prime of c, if we go back and look at the theorem, that's going to be where that's equal to 0. Okay, so we'll use our ruler to draw a nice straight line. And this will be our first derivative here. This will be f prime. I'm going to put my points on here. Negative 4. And let's say we call this 0. We're not going to mark it, but we'll just say if that's where 0 is, this might be 5. Okay. So we know we have some kind of, we have a critical numbers here, so let's see what's happening. Now we could put these values, we could put like minus 5 and 0 and 6 in here, and we can see what we have. But if we're going to use the second derivative test, sometimes that's a little bit easier. Sometimes, especially if this is even more complicated with a lot of fractions, we don't want to substitute numbers in. The second derivative test isn't too bad. Now let's take a look at the second derivative, and I try to do that over here on the side so we have a little more room so you can see what's going on. So what's f double prime? Well, that's just going to be 2x minus 1. And again, that's going to be equal to 0. And that's going to now that's our second derivative. So that tells us about our concavity, and where it is equal to 0 is the point of inflection. So let's find the point of inflection. So we can say 2x minus 1. So therefore, if I add 1 to both sides and divide by 2, I get x equals 1/2. That's my point of inflection. So let's do our second derivative test. And I'm going to do that right below the first derivative so you can see what's happening. And I'll try to line up the numbers. Okay, so we'll do it like this. Okay. And we know underneath here, this is -4, although that's not a critical number. This is -4. And there's 0. This is about where they line up, and this is 5. But my critical number, or my possible point of inflection, now I have to have a change of concavity, so let's check that, is 1/2. So it looks like 1/2 would be right about here. So I'll mark that right here at 1/2. Now let's just check and see if it is indeed a point of inflection. If we have a concavity change, we need to check that. And over here, I can put 0 in, and if I put 0 in, I've got negative, so that's easy. And then if I put 1 in, oh, I put 5 in, I can put 5 in, doesn't matter. 2 times 5 is 10, minus 1, that's definitely positive, so I definitely have a point of inflection because concavity changes. All right, so what we can do now is we said this before, remember, this is negative, so I'm concave down, so I'm going to look something like this. There's my point of inflection. And now this is positive, so I'm going to be concave up. So I'm going to look something like this. So even if you forget, you can see that this 5 here will be down here at the bottom of this little smile. And the -4 will be up here at the top of this smile. So it looks like we're going to have at -4 a relative maximum, and at 5 a relative minimum. So I think that's easy to see. So we have to kind of formally state it, so we have to write all this stuff down over here. So we can say we have a relative max at x equals -4 because because what? Because f prime of -4 equals 0. And f double prime of -4 is less than 0. Okay, and that's just using the statement of Theorem 5, okay? In other words, f prime of 4 equals 0, and f prime of -4 equals 0, and f double prime of -4 is less than 0, so we have a relative max, see? Or local maximum, see, equal. So we're just using that there. Okay, and then we'd say we have a relative minimum, or local. Same thing. Almost the same thing. It's greater than 0. Oh, let me get it. room here. So now we have a relative minimum at x equals 5 because f prime of 5 equals 0 and f double prime of 5 is greater than 0. Okay, so we have a relative minimum, okay? And again, with little sketches here, you can see that. Okay? Negative, concave down, relative maximum. Positive, concave up, relative minimum. And again, we're just using the second derivative test, okay? And you could graph that, and if you graph it, you'll see that it makes sense. You can put it in your calculator. And that's what I did over here. And I graphed it like this, so, oops, let's get the glare out of there. There you go, I think you can see the glare. Okay, this is I put in the calculator like this, so maybe you can see how we do that. Okay, and then when I graphed it, there's your relative maximum where it's concave down, and relative minimum where it's concave up. Okay, see it right there, okay? Relative max, relative minimum. If you trace it out, you'll get those values for x. And you can see that your point of inflection is right about here at about a 1/2, okay? My window, just in case you want to know my window, I had to make a scale of 10 for the y and go from negative 100 to 100, okay? So there's a bit there that you can do with that. I hope that helps. And those will be the last few problems in that section.